In this recording, we will look at some examples of using the power rule for calculating derivatives. First, let's recall that the power rule states that the derivative of a power function, x to the power n, equals n times x to the power n minus 1. In the ddx notations for the derivative, the rule will say d dx of x to the power n equals n times x to the power n minus 1. Some basic examples of using the power rule. So for instance, if we look at the derivative of just x, which is also x to the power 1, then applying this power rule, we get 1 times x to the power 1 minus 1. In other words, 1 times x to the power 0. And remembering that x to the power 0 is 1, we find that the derivative of x is equal to 1. Similarly, the derivative of x squared comes out to be equal to 2x. The derivative of x cubed, 3x squared. If we take a higher power of x, let's say x to the power 10, then the derivative is 10x to the power 9. It's important to know that the power rule applies not only for powers with positive integer exponents, but also to powers with negative exponents, with fractional exponents, and in fact, with any exponents. Here is an example with a power rule being applied to a function which is a power of x with a negative exponent. Let's look at the derivative of 1 over x. 1 over x can be written as x to the power negative 1, and so it's also a power function. And applying the power rule, we get negative 1 times x to the power negative 2. Remembering that x to the power negative 2 is 1 over x squared, we find that the derivative of 1 over x equals negative 1 over x squared. Here's another example, the derivative of 1 over x cubed. If we rewrite 1 over x cubed as x to the power negative 3, then we can apply the power rule to find the derivative of this function to be negative 3 times x to the negative 4. And rewriting x to the power negative 4 as 1 over x to the power positive 4, we find that the derivative of 1 over x cubed equals negative 3 over x to the power 4. Now, let's look at some examples of applying the power rule to powers with fractional exponents. These are often written as radicals. For instance, the derivative of square root of x we can find using the power rule if we remember that square root of x can be written as x to the power 1/2. And so again, it's a power of x. Applying the power rule, we find that this derivative equals 1/2 times x to the power 1/2 minus 1. In other words, 1/2 times x to the power negative 1/2. Rewriting the negative power of x as 1 over x to the power positive 1/2, we find that this derivative is 1 over 2x to the power 1/2. And then finally, replacing x to the power 1/2 with the square root of x, our final result for the derivative of square root of x is 1 over 2 times square root of x. Similar example with a more complicated radical, cube root of x squared, we can rewrite this as x to the power 2/3. Applying the power rule, we find that the derivative of this function equals 2/3 x to the power 2/3 minus 1. And then, so this is 2/3 x to the power negative 1/3, or 2 over 3x to the power positive 1/3. And then we can rewrite x to the power 1/3 as cube root of x. Overall, this derivative is equal to 2 over 3 cube root of x. Here's an example with an arbitrary exponent, 1 over x raised to the power square root of 2. Rewriting this fraction as x to the power negative square root of 2, we can again apply the power rule define that the derivative equals negative square root of 2x to the power negative square root of 2 minus 1. And then we can rewrite that as a fraction. Let's now work through the following example where we compute the derivative of a more complicated function. It's a sum of two terms. Now, remembering that when we differentiate a sum, we can differentiate term by term according to the sum rule. We can then compute this derivative by first rewriting the function as a combination of powers of x. The first term, 5 over x cubed, we can rewrite that as 5 times x to the power negative 3. Second term, 9x to the power cube root of x to the power 7, we can rewrite as x to the power 7/3. And now when we compute the derivative, we can compute this derivative term by term. And also we can apply the constant rule, which says that if we have a multiplicative factor in our function, we can factor that out of the derivative. In other words, the derivative of 5x to the power negative 3 will be 5 times negative 3 times x to the power negative 4. And similarly for the second term, so plus 9 times 7/3 times x to the power 7/3 minus 1. Now let's clean this up. 5 times negative 3, negative 15 times x to the power negative 4 plus 9 times 7/3, that's 21. 7/3 minus 1, that's 4/3, so plus 21 times x to the power 4/3. And we can in principle leave the answer this way, but since the original function was formulated without using fractional exponents and without using negative exponents, we can rewrite our answer in the form that is similar to how the original function was written. In other words, we will rewrite the first term as negative 15 over x to the power 4, and then the second term plus 21 cube root of x to the power 4. Let's do one more example, and this is looks like a fairly complicated derivative. It's a fraction. We have 5x squared minus 4 in the numerator and a cube root of x in the denominator. And one way to compute this derivative is to apply the quotient rule, which tells us how to differentiate fractions. However, there is an easier way to compute this derivative. If you see that this function can be rewritten as a combination of powers of x, then we will not have to use the quotient rule. We'll just be able to compute the derivative using the power rule, the sum rule, and the constant rule. So let's begin by rewriting the cube root of x as x to the power 1/3. And next, let's go ahead and divide the two terms in the numerator by the denominator. In other words, I'll split the fraction into two fractions. 5x to the power 4 over x to the power 1/3 minus 4 over x to the power 1/3. Next, let's remember the rule from college algebra, which says that when we divide two powers of the same variable, in this case x, the exponents get subtracted. So the first term in parentheses will be equal to 5x to the power 4 minus 1/3. I'm subtracting the exponents. Similarly, for the second term, we don't have x in the numerator, but we can think of x to the power 0 being in the numerator. Similar rule gives us that the second term is negative 4x to the power negative 1/3. Let's next compute 4 minus 1/3 for the exponent of that first term. Making common denominator, we find that that first exponent is 11 thirds. So 5x to the power 11 thirds minus 4x to the power negative 1/3. And now we can differentiate term by term, taking the constants out of the derivative and applying the power rule. And so that's going to give us 5 times 11 thirds times x to the power 11 thirds minus 1 minus 4 times negative 1/3 times x to the power negative 1/3 minus 1. And so this gives us 55 thirds x to the power 8 thirds plus 4 thirds x to the power negative 4 thirds. And then we can further rewrite this answer using radicals and fractions. So 55 thirds cube root of x to the power 8 plus 4 over 3 cube root of x to the power 4. And the radical is in the denominator because of the negative exponent. And so you can see that using the power rule, we can compute fairly complicated derivatives.